Hello everyone, so in this video I'll be talking about some important points related to orthogonal diagonalizability and diagonalizability. So the first thing we want to note is that when a matrix is orthogonal, it means that A transpose equals to A inverse, which implies that if you multiply both sides by A, you get A transpose equals to 1. This is the first condition of being orthogonal. Another way of looking at it is taking a look at the columns and the rows of a matrix. And these have to form an orthonormal set. So an orthonormal set is actually just an orthogonal set composed of unit vectors. So what does that mean? So let's say I have v1 is equal to 1, 0, 1, and v2 is equal to 2, 2, minus 2. Of course, if you do v1 dot v2, if you do the dot product of these, you'll get 2 plus 0 minus 2, which is 0. But this is an orthogonal set. So for example, if we had a matrix that was composed of these two vectors as column vectors, it wouldn't be an orthogonal matrix, even though it's composed of orthogonal column vectors. What we actually need is orthonormal column vectors. So we would have to normalize each of these vectors. And how we do that is we say q1 is the normalized version of vector 1, and it's equal to v1 over the length of v1. So all we're doing is we're taking the orthogonal vectors and we're dividing it by its length to get a unit vector that's also orthogonal. So this would just be, so the length is actually just square root of 1 squared plus 1 squared, which is 1 over root 2. So you divide each of the vector components by root 2. And similarly for q2, which is the normalized vector for v2, the second column vector, we would have v2 over length of v2. And as we remember, length is just squaring each of the term, adding it together, and then square rooting the entire thing. So 4 plus negative 2 squared is 4. That would be square root of 12. So it's 1 over square root of 12 is just 2 root 3, multiplied by the original column vector that's orthogonal but not orthonormal. So we basically have to divide each of the components by 2 times root 3. So that's 1 over root 3, 1 over root 3, and negative 1 over root 3. If you find the lengths of q1 and q2, you'll notice that they're both unit vectors, and they preserve the idea that q1 dot q2 is 0, meaning that they are orthogonal. So the interesting thing here is that an orthogonal matrix is actually composed of orthonormal column vectors and row vectors as well. So it's a bit counterintuitive to think of the idea that an orthogonal matrix is composed of orthonormal column vectors and row vectors, but that's just how it's defined. So there's two important things to remember: that A transpose equals A inverse for an orthogonal matrix, and the second thing is that the columns and rows of an orthogonal matrix form an orthonormal set, meaning they're unit vectors, and they also, when you dot it to any other column, or in the case of the row vectors, if you dot any row vector to another row vector, it must equal 0. So now let's get to the two cases for a matrix to be diagonalizable. And actually, before I go into this, I actually want to quickly just touch on what it means for a matrix to be orthogonally diagonalizable, because that case is actually very simple. There's a theorem called spectral theorem. And what this theorem says is that if a matrix is orthogonally diagonalizable, then there's a two-way condition, if and only if A, which is the matrix, is symmetric. Meaning that if A is symmetric, you can conclude that it has to be orthogonally diagonalizable and vice versa. So I'm going to quickly write what it means to be symmetric. A equals A transpose. And there's also a definition for orthogonal diagonalizability, which is an extension of the definition of diagonalizability. So I'm going to quickly write what it means to be diagonalizable. And then you can see that if a matrix is orthogonally diagonalizable, it implies that it's diagonalizable, but it doesn't work the other way around. So with spectral theorem, you can see that if A is symmetric, it implies that it's orthogonally diagonalizable, and this condition is a two-way street. So if a matrix is orthogonally diagonalizable, it must be symmetric. So the important distinction here is that diagonalizability is defined by this equation, in which you have the original matrix A, a matrix D, which has its eigenvectors, or eigenvalues, on the diagonal, and a matrix P, which has to be invertible, because you see the equation is P inverse AP equals D. All it means when a matrix is diagonalizable is that there is a matrix P that's invertible, in which you take each of the eigenvalues and you solve for the eigenspace or the eigenvectors. It's the same thing. The eigenspace is the same as the eigenvectors corresponding to each of the eigenvalues. So if this doesn't make sense, I'll try to cover it in more detail a little bit later. But to actually find the eigenvalues, all you have to solve is the characteristic polynomial given by determinant of A minus lambda I. It's denoted like this. And to solve the eigenvectors corresponding to each eigenvalue, you simply have to solve the null space of A minus lambda I, in which you plug in each value of lambda into this equation, and you'll get corresponding eigenvectors. So if this is the eigenvector corresponding to lambda 1, we'll have all these eigenvectors as the columns of P. So now let's get back to explaining what the spectral theorem entails. I'm going to quickly write down the definition of orthogonally diagonalizable matrices, in which there is a second condition for P. So typically, for a diagonalizable matrix, we just have to check that P is invertible. But for an orthogonally diagonalizable matrix, P has to be invertible and it has to be orthogonal. And let's remind ourselves what it means to be orthogonal. It means that A inverse equals A transpose, and it means that the columns and rows form an orthonormal set, meaning they're unit vectors, and if you dot product any column to another column vector, or any row to another row vector, you'll get 0. From this, you can see that orthogonally diagonalizable implies diagonalizable. So if a matrix is symmetric, you know by spectral theorem that it's orthogonally diagonalizable, and because it's orthogonally diagonalizable, it means it's also diagonalizable. And the reason for that is because the P in this equation is invertible and orthogonal, but the P in this equation is only invertible. And clearly you can see that invertibility plus orthogonality is basically an umbrella over invertibility. I can sort of explain it like this. Imagine this big circle includes invertibility, meaning that P has an inverse. And there's also another block that basically says that P inverse equals P transpose, which is the definition of orthogonality. So orthogonal diagonalizable includes the entire circle, but diagonalizable only includes this quadrant of the circle. So orthogonal diagonalizability implies diagonalizability. All right, so one other thing I wanted to mention is that if you see a matrix such as 1, 1, 2, 2, you can see that when you swap the rows and columns, you'll get the exact same matrix. And what you can conclude from that is a few things. By spectral theorem, you know that it's symmetric, so therefore orthogonally diagonalizable. And since we just proved that orthogonally diagonalizable implies diagonalizable, we can also prove that this is also diagonalizable. And one other quick thing I'll mention is that this is sort of intuitive from the name. If you have a diagonal matrix, it's diagonalizable. And the reason for that is you have the equation P inverse AP equals D. And all you can do is set P equals to identity. So identity inverse A identity equals D. So when you multiply by the inverse of identity, or the identity itself, you'll get back the original matrix, A equals D. Well, is this true? Well, we know A is already diagonal, so A must equal D, and this is satisfied. So thus, we basically prove that if a matrix is already diagonal, it implies that it's diagonalizable. Next, let's go through how to check if a matrix is diagonalizable. This is actually not very difficult. There's only two cases we have to know. And the first case is very easy. So case one is when, let's say, you have the characteristic polynomial, and let's just say we have lambda minus 1, lambda minus 2, lambda minus 3. And you have a 3 by 3 matrix. If you have a 3 by 3 matrix and you have 3 distinct eigenvalues, this is super important because it's the most simple case, but it's also the most common case, is when you have 3 distinct eigenvalues, you immediately know that A is diagonalizable. You don't have to check anything else. And why is that? Well, the explanation is a little bit more convoluted, but there is a theorem that says that the algebraic multiplicity is always greater or equal to the geometric multiplicity. So let's remind ourselves what the algebraic multiplicity means for a characteristic polynomial. Let's also remind ourselves that the characteristic polynomial is simply subtracting lambda along the diagonal. So it's the determinant of A minus lambda I. So the algebraic multiplicity is simply the power of each of these terms. And we can see in this case, the algebraic multiplicity of lambda equals 1, lambda equals 2, and lambda equals 3 is 1 for each of them. Combining this with the theorem that the geometric multiplicity is always less than or equal to the algebraic multiplicity, and the fact that when we solve the null space of A minus lambda I, there always has to be at least one free variable, because basically for each eigenvalue, there has to be infinite number of eigenvectors corresponding to a single eigenvalue. And the best way to explain that is basically you'll always get a span of some kind of vector. And span basically means all possible linear combinations, or all values of a scalar times a vector. I'm not sure if I explained that very clearly, but there's two theorems that we are combining to prove that we don't even have to go further to check multiplicities once we're given a number of distinct eigenvalues. So we're combining two theorems. The first theorem is saying that the geometric multiplicity is always less than or equal to the algebraic multiplicity, which is 1. And the second theorem, which says that the geometric multiplicity has to be at least 1 or greater. So if you combine those two things, we can deduce that the geometric multiplicity for algebraic multiplicity 1 has to be 1. And what does this mean? Well, there's another theorem that says that if a matrix is diagonalizable, the algebraic and geometric multiplicities must be equal. And this brings us to case 2. So for case 1, if you have an n by n matrix, and you have n distinct eigenvalues, you immediately know it's diagonalizable. Case 2 is a little bit trickier. It's when we have repeated eigenvalues. So let's take a look at this example. We have an upper triangular matrix, meaning that the eigenvalues are simply the values along the diagonal. And this applies for when you have an upper triangular matrix, a lower triangular matrix, or a diagonal matrix. You can simply read off the eigenvalues off the diagonal. So if we write the characteristic polynomial, which is the determinant of a minus lambda I, we'll get lambda minus 1 cubed. And as we mentioned before, this power is the algebraic multiplicity. Okay? So based on the theorem I just told you, the geometric multiplicity has to be equal to the algebraic multiplicity in order for this matrix to be diagonalizable. Well, we know how to calculate the geometric multiplicity. It's actually just the dimension of the eigenspace. So that may sound complicated, but what that actually means is just computing the eigenvalue of this matrix. And how we do that is we find the null space of a minus lambda I. Let's remind ourselves that the null space is just the solution set of ax equals 0, where x is non-zero because eigenvectors have to be non-zero. And just refreshing your memory, when we're talking about a subspace, it has to include the zero vector, and it has a bunch of other conditions such as closed under vector addition and closed under scalar multiplication. But we know that the eigenvectors themselves can't actually form a subspace because it's non-zero by definition. But then you have the eigenspace, which includes 0 plus all the eigenvectors, and that will be a subspace, but that's besides the point. Let's get back to solving this and checking if this is diagonalizable. So again, case 2 is when we have non-distinct eigenvalues. And let's solve this simply by solving this equation. 0, 1, 0, 0, 0, 1, and we augment with zeros. And let's plug in 1, since that's our eigenvalue. So we'll get 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. So actually from this matrix, I can already tell that it's not diagonalizable, because in order to get geometric multiplicity of 3, it actually has to be the zero matrix, because the geometric multiplicity corresponds to the number of free variables. And this clearly has rank of 1, because there's 3 columns and there's 2 free variables. This means that based on the number of free variables, the geometric multiplicity is 2. And since 2 is not equal to 3, we can conclude that this matrix is not diagonalizable, since the algebraic and geometric multiplicities for each of the eigenvalues have to be checked to be equal. The other point I want to quickly bring up, as I already mentioned before, is if you have an algebraic multiplicity equal to 1, we actually don't have to check the geometric multiplicity because we're combining 2 theorems here. The first theorem is saying that geometric multiplicity is always less than or equal to algebraic. The second theorem is saying that the geometric multiplicity is always greater or equal to 1. And this is because a single eigenvalue forms a span of solutions, which is defined by an eigenvector, which means that there has to be at least one free variable in order for it to form a span of solutions as opposed to a single solution or no solutions. So combining this geometric multiplicity less than algebraic multiplicity, which is 1 in this case, and geometric multiplicity has to be greater or equal to 1, we can conclude that whenever we have an eigenvalue that has a multiplicity, an algebraic multiplicity of 1, it means the geometric multiplicity has to be 1. And that will save us a lot of time when we reach case 2. For example, if we have a characteristic polynomial for case 2 where we have non-distinct eigenvalues, such as this, each of these algebraic multiplicities is actually just going to be 1. And what does that mean? Based on the last theorem, we showed that the geometric multiplicities of all of these has to be 1. Meaning that in order for this matrix to be diagonalizable, we just have to check the null space of A minus lambda I for lambda equals 1. And we just have to verify that geometric multiplicity is equal to 2. All of these values are distinct, and they have algebraic multiplicity 1, meaning that the geometric multiplicity has to equal the algebraic multiplicity. And that simplifies our calculation a lot. Unless we have to find P, of course, in which we have to solve all of the eigenvectors corresponding to the eigenvalues. But I'll be explaining that in the next video.